Hey everyone, welcome back to From YAML to Production, a Kubernetes podcast. I'm Maria, here again with Christo, our host. And in the last episode, we covered how a Kubernetes cluster is actually built. We covered the control plane, the infrastructure preparation, and the installation sequence. Today, this is episode 3, and this episode is all about the storage.
Hi everyone, this is exactly the topic I promised at the end of our last episode. So let's deliver. Networking explains how packets find their way between pods, and cluster architecture explains who makes the decisions. Storage explains how your data actually survives when everything else restarts.
This episode is a highlights tour. We're covering the key concepts and lessons from Christo's full blog article, which is linked in the show notes. If you want the deep dive with YAML examples, diagrams, and even exam references, that's the place to go. Let's start with the foundation. Kubernetes was built for stateless workloads. What does that mean in practice?
Stateless containers follow three principles, Maria. So they're ephemeral, idempotent, and immutable. In plain English, they are short-lived, repeatable, and never modified in place. They just get replaced with the new version. That model is exactly what makes Kubernetes so good at scaling and self-healing. If a node suddenly disappears, the workloads just reschedule elsewhere. Everything heals through the replacement.
But the moment you introduce a database, that entire model breaks down.
Exactly. You can't just replace data the way you can recreate a container image. Data has to survive pod restarts, node failures, cluster upgrades, and rescheduling. Kubernetes has to reconcile its highly disposable compute model and with absolute permanence that stateful workloads require. That reconciliation process is where most of the of your production complexity lives.
So is running stateful workloads on Kubernetes considered mainstream now?
Absolutely. It used to be highly experimental, but today it's the standard. However, doing it well requires you to truly understand how Kubernetes models storage internally. That understanding is what separates operators from who can actually debug a storage failure from those who can only follow a runbook.
Walk us through how Kubernetes actually models that storage.
It does it in layers, Maria. At the lowest level, you have volumes. These are defined right in the pod specs, and their lifecycle is strictly tied to the pod. Where we are talking about things like emptyDir from empty directory, or for scratch spaces, or mounting config maps and secrets. They are ephemeral by design. One you really want to avoid in production is hostPath, which mounts a directory from the node's file system directly into the pod. That totally breaks pod mobility and introduces container escape risks. It's a common exam topic for a good reason.
So for persistent storage, you need something above that layer.
That's where persistent volumes, or PVs, come in. A persistent volume is a cluster-scoped resource that represents a real piece of storage, like a GCP persistent disk, an NFS share, or a local disk. It completely abstracts the underlying hardware. But workloads don't talk to persistent volumes directly. Instead, they use persistent volume claims, or PVCs. A PVC is basically a namespace scoped request where the developers say, hey, give me 100 gigabytes of read-write once storage from the fast SSD storage class. Kubernetes then takes that claim, finds or provision a matching persistent volume, and binds the two together.
And the storage class sits above all of that.
Right. The storage class is essentially the blueprint. It tells Kubernetes exactly how to provision the storage, like which driver to use, and most importantly, the binding mode. The setting, wait for the first consumer, is a lifesaver here. It tells the cluster to hold off on creating the disk until the pod is actually scheduled. Guarantee the storage is created in the exact same physical location where the pod lands. If you just provision the disk immediately, it might end up separated from your pod, leaving you with attachment error.
What's the most common mistake that people make with PVCs?
It's assuming that if you delete and recreate persistent volume claim, it will with the exact same specs, it will automatically rebind it to the same persistent volume. It won't. It's unless that PV was set to retain and you want and manually clear it. It's not going to reattach. It's a classic gotcha on the certification, and unfortunately a very common cause for real-world production incidents.
Let's talk about the CSI, the Container Storage Interface. What is it and why does it matter so much?
Before Container Storage Interface came along, storage drivers were compiled directly into the core Kubernetes binary. If you want to add a new storage backend, you literally had to wait for a new Kubernetes release. It was totally unsuitable. CSI moves those drivers out of the code base entirely. Now storage vendors ship their drivers as standalone pods inside the cluster. Kubernetes just speaks to the CSI spec over remote procedure call, and the driver handles all of the vendor-specific heavy lifting.
What does a CSI driver actually look like when it is running inside the cluster?
It's usually split into two workload types. First one is when you have a controller plugin. It's typically running as a deployment, which handles cluster-level operations like provisioning, deletion, attachment, and taking snapshots. Then you have node plugin, deployed as a daemon set, which runs on every single node. That handles the node local operations, staging the volume, mounting it into the pod, and unmounting it when the pod stops. When you're looking at the CSI driver logs during a storage failure, knowing which component handles which phase tells you exactly where to look.
StatefulSets are closely tied to Container Storage Interface and to persistent storage. Can you explain the key pieces the people need to understand?
It all comes down to volume claim templates field. Instead of referencing a single shared PVC, each pod in a stateful set gets its own individual PVC created automatically from that template. So the naming is completely deterministic in that way. We having data like data Postgres 0, data Postgres 1, data Postgres 2, and etc. If Postgres 1 gets deleted and rescheduled, it automatically finds and reattached to data Postgres 1. The data is never lost because the name is perfectly predictable and the PVC outlives the pod. That stable identity is also what allows cluster databases to bootstrap correctly, because every node always knows exactly who its peers are.
What are the most important production considerations beyond just getting the storage to attach and to work?
There are really four main areas, Maria. First one is the encryption. By default, Kubernetes does not encrypt etcd or persistent volume data. You have to configure storage layer encryption at the storage class level, and you have to separately configure an encryption configuration for secrets at rest and etcd. Those are two totally different mechanisms. Second is FS group in the security context. If your container runs as a non-root, it might not have permissions to write to a mounted volume that's owned by the root. Setting an FS group instructs the kubelet to change the ownership of the volume to the right group and before the container starts.
What about on the resource management side?
You absolutely need resource quotas for your storage. Without them, a single misconfigured workload can completely exhaust your storage capacity. You can cap total storage request per namespace, limit the total number of PVCs, and even apply separate limits per storage class. That way your expensive fast SSD tier gets its own independent quota from your cheaper, slower storage tiers.
Thank you, Hristo. Walking through the abstraction stack really makes Kubernetes storage feel a lot more approachable. The PVC requests the storage, the persistent volume represents it, the storage class defines how it is provisioned, and the CSI drives the actual operations underneath.
Exactly, Maria. Once you understand that chain, every single storage operation becomes predictable. And when you're working in production, it is just as much about understanding the failure modes as the happy paths. Reclaim policies, quotas, encryption, security context. Those aren't optional extras anymore. They're the difference between a system that recovers gracefully and the one that loses your data.
This has been from Yamamoto Production, a Kubernetes podcast. Please subscribe and share if you found this episode helpful. And remember, the full article is linked in the show notes, complete with YAML examples, even diagrams, troubleshooting, flowcharts, and a dedicated exam reference section.
Goodbye.
See you in the next episode.